There we are. Matt, do you only have audio?
I'm working on it, but
Not a big
for some
deal.
reason it might just be audio.
Okay. Are you guys getting super echo from Matt talking there? Coleman?
Not really.
Okay.
Mm-mm.
See here. We got Jordan.
Hello.
Hey Jordan, did Professor Cote get back to you?
No.
He hasn't? All right,
No.
I'll get a hold of him.
Okay, thank you.
Yep. Journey. That is. Cool. We got Will.
Yep. Edie should be in a second.
Matt, you haven't heard from Kira today, have you?
No, I haven't.
It just occurred to me I haven't either, so it's
Oh.
possible she has a power issue.
She just joined.
Oh, she did? Okay, good. $31. Badini. Jasmine will be back. All right. Get started. Limbo. Peter. Haley Jasmine. I guess we will get started. Surprised we're missing Trinity. Wait. They might be. Yeah, there we go. Jasmine, how was your debate trip?
It did pretty poorly, actually.
Oh, yeah?
Yeah.
I'm sorry.
It was not a good tournament for us.
I'm sorry about that. But
Oh, it's fine. It was nice.
we got Kira. All right, I'll fix attendance later. All right, we'll get started. So a couple things up front. I've tried to sequester my 3-year-old twins, but they're 3-year-old twins who can't go outside. So hopefully they won't come in screaming. We'll see. The other thing, I think I practiced with the tech a little bit earlier today, so I think I've got it figured out in order to be able to like share whiteboard stuff with you and all of that. I might run into some extra speed bumps in that process, so sorry about that. And you don't have to get into it right now, but please contact me if you have any issues with getting the individual quiz working, or if you have trouble getting in touch with those group members by Friday, either because of weather issues for us up here in the north, or just because it's difficult to actually get to work at all. I've never done this before, so it could be stricken with problems I did not anticipate. So just be communicative if you have problems. I'm not looking to make people's lives hard. But your academic liaisons should have gotten the individual quiz. Each of them should have gotten a copy. It was a PDF, so they shouldn't have trouble opening it. If you haven't heard from them, let me know, and we'll figure something out. Okay. So a couple of bookkeeping things. The new assignment sheet is up. I did better getting that done today than I thought I would. I did spend 3.5 hours clearing my driveway, and I genuinely had icicles hanging from my beard that had grown. It was pretty awesome. I didn't know that happened, but apparently that's a thing. So it's up, and let me show you a few things on it, because there's some cool stuff and some stuff that I think you'd have questions on. Here we are. Are you guys seeing the assignment sheet now?
Yes.
Yep.
Yeah.
Okay. So here we are on Tuesday. No homework besides working on your quiz. You do have, if you look here, you do have 2 more chapters in relativity to read. I will offer that I think because he's kind of laid the groundwork at this point, this is way into the book, chapters 19 and 20. I think they're a lot better, a lot more digestible, kind of oddly. They're much better than the early chapters that you read, so I don't think they'll be quite as laborious as the early stuff. The next thing, I sent an email. You can see the red there. I sent an email a while back asking you to get a copy of 6 Not So Easy Pieces by Richard Feynman. It's a tiny little book. My copy's at school, but like of this size, it's like $12 or something. You can get a digital copy. Also, if your library might have it, your library also might have the Feynman lectures. And 6 Not So Easy Pieces is actually just an excerpt of 6 lectures from this book. If they have the Feynman lectures, and not 6 Not So Easy Pieces, I put the chapter. It's chapter 42 of volume 2. That's on the assignment sheet as well. You don't have to read the whole thing. You're reading through the section "Our Space is Curved." If you want to read further, he does start to get much more into the math than I'm going to get, and you might enjoy that if you want to dig deeper. It's a really great lecture. Let me come back to where I can see you. Okay. How many people have read some of Feynman's stuff before, or stuff on Feynman?
Here.
Okay. He's kind of partially most famous in the physics community for this. Is that backwards to you?
No.
Okay, it is to me. Quantum electrodynamics. I think he was being clever when he named it QED, Quod Erat Demonstrandum. Anyway, he won the Nobel Prize for his work on that. But he's kind of more famous in popular culture for being coined. He was the smartest man in the world. When his wife was dying of cancer, he essentially made himself a doctor to re-diagnose her. He solved, with some help, the Challenger disaster when that shuttle exploded. But he was also known as physics' greatest teacher. And his stuff is really cool. If you're a big Feynman fan or you become one, I recommend this thing, Feynman's Lost Lecture. What's unique about it, it's one of the lectures that didn't make it into the lecture series. And what it is you may not know this, but in Newton's time, algebra was not accepted as proof of Newton. And so he goes ahead when a bunch of other kids were had some other exam. He took the ones who were left over, and he proved the elliptical orbits of the planets only with right triangles in geometry, with no algebra. And this has what he drew on the board in it, and also a recording of him actually giving the lecture, and it's pretty amazing. If you know nothing about Feynman, this might sound a little funny, but I highly recommend the graphic novel called Feynman. It's really cool. I forgot to mention he also worked on the Manhattan Project and the development of the first nuclear weapon. A really cool guy. So check those out. And if you have trouble getting a hold of the lecture I'm talking about, let me know. I was kind of trying to avoid doing anything illegal and sharing a PDF photocopy of it. Relativity is public domain, so I felt comfortable doing that. But if you really have trouble, I might be able to work something out for you. Other things on the assignment sheet, and then we'll move on to maybe the coolest thing we've talked about by a wide margin. Yeah. Are you guys back to the assignment sheet?
No. We're not. Oh,
No?
Oh, yep.
Yeah, we are.
Okay, good. Friday, I didn't give you anything to do, just to guarantee a free night, that a free day where you might be able to meet with your group. Let's see here. Then the other thing that you'll have questions on, this, you can feel free to at this point. I use some of Henry Reich's videos in this assignment sheet, and we'll use some in the future, but you should feel free to really explore the Minute Physics channel. He has really beautiful videos about things in contemporary physics and things in classical physics. I think my favorite is his series on what the Higgs boson is. The videos are great. He's a cool guy, and I'm really excited. He has agreed to come visit us officially in early February. I have not heard back from him. I offered him Tuesday the 3rd. It might be that he wants Friday the 6th or something like that. But as far as right now, Henry's going to join us for class on Tuesday the 3rd, if possible. The thing you might have a question on is over here. This is really long, but it's not actually that intimidating. This next unit is in kind of 2 subparts. The first being general relativity, which is amongst the hardest thing that a person can ever study. And we're going to mostly just have fun with it. When we get to the end, some really cool topics that are connected with it are listed right here. Things like dark matter, dark energy, gravity waves, the speed of light in the early universe, stuff like that. So we're gonna take sort of a qualitative look with some quantitative pieces at general relativity. And then at the end, what I wanted you to do is just pick one of these topics, or if you have something else that you're interested in that you think is connected with this. Obviously, Jasmine, since you're into astronomy, you might have something that's not on this list that you might be really interested in pursuing. That's fine. I'm just inviting you to hop online, look stuff up about it with a little bit of, look for the names of universities and the URLs of stuff you're reading. Wikipedia is too good. It will melt your brain. A lot of it is way too accurate for you to digest. Written by theoretical physicists all over the world, and it's just incomprehensible to most people. And the simple Wikipedia versions are nothing. So things like hyperphysics and things like publications from universities are pretty cool. I'm just looking to eventually have you, tell us a little bit of stuff about it in our following class on that Friday, about stuff that you found out about it. Why am I doing this? End of the semester, what we will be doing is doing our own research projects, and these topics in general relativity have tended to be the most popular, and I'm just seizing this opportunity for you to get a quick look at it because, for example, I've had students be really into gravity waves, decide to do that as their final project, and get just crushed by it, and needing to change their minds at the last minute. So this will give you a little bit of an early view and not be terribly stressful. Let's see here. And the last thing that you might have when we get to the end here, our second half of this unit is on this laundry list of experiments that led to the quantum model. And there are tons of little equations, and most classes kind of force you to do plug and chug with those equations, and that's where they end it. And I will make you do some of that on some worksheets here. This worksheet is kind of cool. It'll have some virtual experiments for you to do, which are kind of fun. But I care much more about why each of those experiments was important and how it contributed to the development of a quantum model. So your actual test will be an interview with me where I will give you a list of 4 questions with cryptic names. You pick one, I'll ask you the question, and then you try to explain it. Don't be nervous. It's a good time. when I do this in my brick and mortar class, it's usually with a small group. And I kind of peg each person with a, like, you answer this question, you answer this question, you answer this question. Okay, now it's open field. Anybody contribute to answer the kind of overarching question. So that's coming. It's not meant to be a source of stress. It's meant to be kind of a more fun way to look at this. So be aware of that in the weeks to come. I think that's all of the bookkeeping for now. We have limited time. If you have logistic issues with your test, email me and we will figure it out. Okay, I'm going to stop sharing this and come back to you. There we are. So, did anybody else get affected by the blizzard that happened in the Northeast? It came from a funny angle. Did it hit you in New York or anything like that?
No, not here.
Not out here.
Not in Texas. I would have. No, not at all.
No.
Okay, cool. Kira and Matt, how'd you fare?
There's a lot of stuff.
It's not as bad as they were promising.
Yeah,
But,
I got
but it's pretty bad.
I got like 20 inches or so. It was pretty impressive.
It's 75 degrees here in Texas.
That sounds pretty cold.
It was bad, but not so bad. We had one last year that was 43 inches where I was, like almost up to my waist. It was awful. Okay, so our next topic, general relativity. Let me. I'm gonna get a whiteboard up here. Share. Okay, I need to share screen. Is that tiny for you?
No,
No, it's good.
No.
that's fine.
Yeah, it's good.
Okay. All right. So I mentioned that relativity is super duper hard. I mean, general relativity is super duper hard. And here's a little bit of why. When you first learned about math, and I mean first learned about math, you were exposed to specific kinds of quantities. Something like this, 1 kilogram or $5 or 3 pieces of pizza. In early math books, I tutor some algebra. Everything is in terms of pizza slices. It's very interesting. But these things you learned later in your physics classes were called scalars. Right? Yes, no?
Yes.
Heard of scalars?
Yeah.
Yep.
These are single pieces of information. Another way to think about them is something with an amount, but nothing else to it. Sometimes people get a little confused because they're like, well, isn't the unit a second piece of information? No. 1 kilogram. A kilogram is essentially a number. Moving on from there, you learned about – what did you learn about next?
Vectors.
Going from scalars, the next step was
Vectors.
vectors. And those were things like velocity or force or something like that. And they had an amount and a direction. They could be represented with an arrow. They could also be represented in a linear algebra way, like that, right? Like a combination of information. Now, this was something that needed one piece of information to identify its components. This requires 2 pieces of information. To explain, Mr. Taylor, you wrote down a 3-dimensional vector here, but it's still a 2 information object. If we look at it, to identify each of its pieces, we need to know what, say, row the information it is in, and then we need to know the value itself. Okay? A vector is a 2-piece of information object that can exist in any number of dimensional spaces, although in its simplest form, as soon as you move to a 2-dimensional space, you kind of need vectors to describe what you're talking about. Then, some of you, not necessarily all of you, but I'm sure at some point in your math education, you learned about what comes after vectors.
Tensors.
Sort of. Well, we're actually technically already in tensors, but you skipped a step.
Matrices.
Yeah, matrices. And 3, 7, 2, 1, 4, 6, 1, 7, 5. These require 3 pieces of information to understand, but they can also represent something that needs 3 pieces of information. You could locate a column and a row and a value. In its simplest application, one could use a matrix to represent a 3-dimensional space, where, say, the row and column, if you made an infinite dimensional matrix, which you can do, could represent a coordinate in the xy plane, and then the value in that cell in the matrix could tell you how high up in the z direction you were. I'm sure that some of you are aware that general relativity requires a 4-dimensional space. So Einstein, and I'm sure with some friends around him, takes these ideas and extends them and creates tensor math. He goes back and he says that this is what's called a, let me get a different color here, a rank 0 tensor. This is called a rank 1 tensor. This is called a rank 2 tensor. And what general relativity will need is a rank 3 tensor, something that could be 4-dimensional. One way to think about what that is a matrix composed of vectors or you could think of it as a cube of information where within there's kind of 3-dimensionally located, I don't mean for these to all be zeros. I'm just locating different places that could have a height, width, depth, and then a value. So that one thing you could do with a rank 3 tensor is represent a 3-dimensional space and layer a 4th dimension on it by assigning a varying value to each of the coordinates in that space. What we need for general relativity to actually do it is essentially to not only have a 3-dimensional space x, y, and z, but to have a changeable value for how long a meter is at that point in space. To say that 4th dimension is time is a little bit erroneous, but sort of true. We will move on from there. So anyway, tensors are difficult and to deal with. Layer onto that you need to layer differential geometries into those tensors. We're talking about math that I'm sure some of you could do, but it's a little bit beyond what we could fit into the time we have. You can spend your life studying this, and many people have. So where are we going to start with our conversation about general relativity? Well, first we have to identify what the heck we're talking about. So far, we have done a special relativity, which has been all about constant velocity. So general relativity is Einstein and others going ahead and saying that v is not constant, and therefore talking about reference frames with acceleration. And even in classical physics, as soon as you go to accelerated reference frames, things get difficult. Think about circular motion, and if you were dealing with, wow, that was impressive. Nice circle. If you were standing on the Earth as the Earth was rotating, and you wanted to transfer yourself into the accelerated reference frame at that point in space, you would actually need to include 4 fictitious forces to make the reference frame transformation. Not just centrifugal force, which I bet you've heard of, but also the Coriolis force, which you might have heard of also, a translational and an azimuthal modification. Accelerated reference frames are hard in classical physics. So what are they going to be like with relativity layered inside? I keep using the word layered. Oops. Leave the 3. So we'll go with a simplified thought experiment. Let's say that we're standing still inside a rocket ship, and that there's a mirror up here, let's say, and there's a little laser over here, and the laser fires, hits the mirror, bounces off, and gets to us. We could say that given an initial velocity v0, that the light took the path of least, well, a whole bunch of things. It took, given that v0, the shortest path that it could take given the initial conditions and the laws of physics. You could say that it took the path of least action, which would make Feynman very happy. You could say that it took the path of least time, given the initial conditions. It took the shortest possible path to you, given the information that it started with, its initial velocity, the presence of the mirror, etc. But what if, as soon as the light were fired, the rocket's engines took off, so that there was a net force up, and so that this thing started to accelerate upwards? What would happen? Yeah, Dallas. Sorry, I can't see everybody for some reason. I can only see Dallas.
Um,
Go ahead, Dallas. Did we lose Matt?
Yeah.
Oh, I think he has a connection issue.
Hello?
Matt?
Let's see.
All right, let me see if I can fix things. Stop sharing. Constant presence. Apply. That's again. All right, go ahead, Matt.
Can you hear me?
Yep.
No? Okay, cool. I was saying that the path of least action is no longer a straight line path. It's going to be bent backwards towards where you're accelerating from.
All right. I mean, one way to think of it simply is that a person standing outside here, I mean, he's right. A person standing outside here has to see this light that has been fired. Think of it as like a single pulse of light that's been fired out. Has to travel in essentially a straight line path towards the person standing outside in a reference frame that has an acceleration of 0. Light would not change its path. So this accelerated reference frame would move up into it so that to the person standing inside the rocket ship, it would appear that the light bent down towards them. In actuality, to a person standing outside, what happened is that the light went straight and the rocket ship moved up into it. And it made what appeared to be a parabolic path simply because the rocket ship itself was increasing its upwards velocity as it went. Does that make any sense? Questions? Yeah, Will. Are you muted?
How would that be different than having a very high constant velocity?
If you had a constant velocity, you would both agree that the light took straight line paths. You disagree about the direction of that straight line path, which is, if you remember back to our time dilation derivation, right? We had we had in one reference frame the light going straight up and straight down, and another reference frame the light going diagonally across the viewpoint. Do you remember that?
Yeah. Yep.
So they'd both be straight lines. Nothing would have been curved. To the constant velocity reference frame, the path of the light is straight. To the accelerated reference frame, the path of the light is curved.
Okay.
Does that answer your question?
Yeah.
Okay. Other questions? Yeah, Matt.
This would still be true if it was like a baseball, not light, right?
Yes, absolutely.
Okay.
Eni.
Is it sort of like when like you're like in a car and then like you throw something up? Like let's say you like threw a baseball up, and if you were accelerating like the path of the baseball, it's sort of like a parabola, like the car accelerates forward. But if you're going constant, it just falls back right in your hand.
Absolutely. Absolutely true. The thing I'm trying to see if you're okay with is that the light appears to take a parabolic path, or an approximately parabolic path, because we're leaving out some details here, to the person in the rocket ship. Do we feel comfortable saying that the person in the rocket ship would see light bent, assuming that acceleration, I mean, obviously, either the rocket ship would have to be 8 billion miles wide, or the rocket ship's acceleration would have to be comically large, right? Because light would get across the ship really fast, but we'd have to have either like ridiculously precise instruments or huge accelerations or a gigantically wide rocket ship for us to witness this curvature. But given one of those things were true, we would see curvature. Is that okay with you?
Yeah.
Yep.
Okay. Now, from there, I'm going to take this moment to make a pit stop on our discussion of this to something else. Go back to Reflector. You guys have a blank screen on my whiteboard thing right now?
Yep.
I remember last time we had a sync issue. It's okay?
Mm-hmm.
Okay. So let's say that this were a completely different scenario. Let's say that what we had, there's no gravity, we're in space, and we've got this flat plane. We've got a bumper and a marble. And the marble starts out with initial velocity v naught. And we're standing, it's a very large marble. We're standing over here. We watch, and the marble bounces off, comes to us like that, taking the path of least time, or actually the path of shortest distance given the initial velocity. That could take it from that point to us given the initial conditions. That's the shortest thing it could have done. But what if the plane that this marble was traveling on wasn't flat to begin with? What if the floor were curved? Like this. We're still standing here. What would the marble do if it had an initial velocity pointing this way this time? Don't worry about why, but what would it do?
It would take a
It
curved path.
would curve downward.
Yeah.
It would take the path of least distance again. It would curve down towards us like that. One way to think about that is through Newton's laws, that there's a normal force that points up like this, and say that there's gravity or something like that pointing down, or right, and that the initial velocity experiences an acceleration that causes its path to arc, or something like that. But another interpretation, a very strange one, but that nonetheless seems to be true, is that this object is taking the shortest path between us. It's not going to go this way, because it would have to go downhill and then back uphill again. it's not going to go this way because it would take such a large distance and it turns out such a large amount of action to get to us. It would take the path that you instinctively know is correct, this arced path. It would follow the curvature of the world it is experiencing so that it travels the path of least distance. When the surface was flat, that answer was to bounce off the wall. As soon as the surface was curved, the answer was to follow the curvature. Okay, what's the point? Hold on to that. Let's jump ahead a little bit. So, how many people... Stop sharing. It always puts me back to active speaker whenever I share my screen. Kind of stinks. Apply. There we go. How many people have heard of the equivalence principle?
I feel like I have.
I know I have, but I can't
Yes.
think of what it is.
Yeah.
Yeah.
What is it?
The crafty.
Oh, yes, I know. I remember.
Go ahead.
So this is a postulate of Einstein's that the laws of physics are exactly the same in a gravitational field as they are at an accelerated reference frame.
Okay. That's exactly where we're heading. But even in classical physics, we can apply an equivalence principle. Let's go with this. I'll go back to sharing. So let's say you decide to go for a drive. Kira, Matt, don't do it. You did badness, snow. So we decide to go for a drive, and as is illegal in Connecticut, you have hanging from your rearview mirror some fuzzy dice. I don't think people have these anymore, but they still show up in physics problems. So you then accelerate your car forward, and what happens to the thing dangling from your rearview mirror? If we zoom in on it, like here's the mirror, here's the string holding. Oops, sorry. Here's the string holding the object. What happens as the car accelerates forward?
It'll appear to
Swings back.
fly towards you.
Yeah, it'll swing back. And actually, if you were to maintain a constant acceleration, which is impossible to do, what will happen is that it will sit at a very particular angle as you accelerate. If you were to travel at constant velocity, it would hang down again. One way to explain how this works is to draw a free body diagram. Say that there's a tension pointing up at some angle theta, and gravity, mg, pointing down like this. And that what is essentially happening is that the vertical component of this tension cancels out the weight, and the horizontal component of this tension supplies the same acceleration as the car. And so what we wind up with is that F net on the thing dangling is ma car, which turns out to be such that, if I remember correctly, we've got mg tan theta, that the, well, sorry, I meant to say is that the tangent of the angle is a over g. As you can kind of see here, you've got ma pulling us forward and something equivalent to the weight pulling up. It makes sense that the tangent of the angle is the ratio of the two things. Yay. That's the way we do it in AP Physics C and other classes like that. A weird way that we could do this is to pretend that we are in the reference frame of this person. What this person might think, and it'd be a very strange scenario, but you still might think this, that really what's happening is that the tension is pointing this way and that gravity has rotated. That gravity now points this way and that the thing is in equilibrium. It's a super weird way to think about it, but if you've ever been, like, there are some amusement park rides where they close off your view so you can't tell what's going on, and they accelerate the object either by tilting it or by actually putting you in a centrifuge and spinning you around, and you feel as if gravity is pointing a different direction. Really what's happening is you've acquired an extra acceleration. But what it feels like is as if your weight is pointing somewhere else all of a sudden. You would get exactly the same result for the angle, etc., by saying equivalently that your added acceleration results in an apparent shift in the direction of gravity. Sorry, my kids are being loud. Where? Okay. It's also, by the way, a useful technique for some really challenging problems. One I can think of now is, let's say you had a wedge with a mass on it, and that the whole thing were accelerating forward, and you wanted to find the acceleration of this object. A really good way to solve the problem is to move into the reference frame of the wedge and pretend that gravity is rotated. It actually gets a lot easier to solve that way. I bring it up because there are some like physics Olympic exams and stuff like that that ask questions of that nature, and it can be useful. So here we go. Let's simplify the scenario and talk about what Jordan was saying. Imagine you are in a room with no windows and no doors. You are standing on the floor, as you know one does, and you look down to a digital scale. And sitting on that digital scale is an object with 1 kilogram printed on it. You look down at the scale and you see that it reads 9.8 newtons. Where do you think you might be?
Earth.
On Earth.
Earth. What evidence do you have?
It's 9.8 newtons.
That the weight is mg is 9.8 newtons. 9.8 times 1 kilogram. You take out your keys, you let go, and you watch it accelerate towards the floor. You see that it accelerates at 9.8 meters per second squared. You are convinced. I am on Earth. Suddenly a slat opens in the side, and you discover that you are in space, which I will denote with yellow stars for no reason. You look out the window, and you somehow see that, in fact, there is no large gravitating body anywhere near you at all, but a cable attached to some winch millions and millions of miles away that you can't see, that is exerting attention on the box that you're standing in, such that the whole thing is accelerating upwards at 9.8 meters per second squared. There is no gravity. What happened to your keys when you saw it fall and hit the floor?
The floor moved up.
Keys.
The floor accelerated up at 9.8 meters per second squared, which to you looked exactly like the object accelerating down. Why did the scale read 9.8 newtons?
Because the scale is moving up.
The scale has to exert, if this is the free body diagram of that 1 kilogram object, there's only one force on it, the force coming from the scale. It must be equal to ma, the acceleration that's being given the object. And since it's accelerating with the box that you're in, that acceleration must be 9.8. So that this force must be 9.8 newtons. Not because of a gravitational field that is pulling on you at 9.8 newtons per kilogram, but so that the object accelerates together. So what is the difference? How can you tell if you're in a gravitational field of 9.8 newtons per kilogram or in a box that's accelerating at 9.8 meters per second squared up?
You can't.
Can't.
What was that?
You can't.
So there's absolutely no way.
You could just look outside.
You can open the
Okay.
window.
You could look outside. You'd have to be able to get other information. knowing the strength of the acceleration or knowing the weight from a scale, none of those things is enough information to tell the difference. Besides what you see with your eyes, what is the experiential difference between accelerating upwards at 9.8 meters per second squared in the vacuum of space and being in a gravitational field of 9.8 newtons per kilogram?
Also nothing.
Nothing. That's what Einstein says. He says that there's no difference. That's what chapter 20 is about. And I've kind of partially explained what he says there. That is the equivalence principle that Jordan was talking about, that you cannot tell the difference between an accelerated reference frame and a reference frame in which there is a gravitational field equal to some other perceived acceleration. So, let me go back to here. Actually, I'll just redraw it. Hold on a second. I'll pull up the drawing in just a second here. So you're standing in a rocket ship. You don't know if it's accelerating upwards at 9.8 or if you're standing in a gravitational field at 9.8. You don't know. You look down, you see the same scale arrangement over here with the 1 kilogram mass sitting on top of it or whatever. And then a laser beam fires a pulse of light. Now, you told me you accepted that if this frame is accelerating upwards at 9.8 meters per second squared, that you would perceive a curved path for that beam of light. You look out the window and you see that, in fact, you are standing on the Earth and that your acceleration relative to that Earth is 0. If Einstein is right, that there is no difference between accelerating and being in the presence of gravity, will the light take a curved path?
Yes.
Does everybody agree, or does anybody have any problems with light taking a curved path because of the presence of a gravitational field? You should have something. There should be some problem.
Oh, wait.
Would it?
Hold on.
No,
I mean, it would make sense.
Yeah, it makes sense.
Yeah.
Will and
Just the
Jack.
fact that light.
Does it matter that light is massless though?
Yeah.
Because gravity affects mass only. They're not only, but
Gravity pulls on mass, according to Isaac Newton, who, to physicists at the time that Einstein says all this stuff, is God. Okay? Gravity acts on mass. Light has no mass. The laws of relativity, special relativity, say it better not have mass, otherwise it cannot possibly be traveling at the speed of light, because it would have infinite energy. Infinite energy is bad. So maybe gravity doesn't act on mass in that way.
What about the stuff like where the gravitational pull of some things is so strong that like light has to go there, like black holes and stuff? Like it isn't acceleration, but it's still curving sometimes. Like there are like areas in space where like it
Why
curves
is it?
around planets and stuff.
Yeah. Why is it that that's where we're heading eventually, gravitational lensing? How can its path curve? It has no mass. It cannot experience force. It cannot experience acceleration. So how can its path be curved to us?
Because
what if space is
gravity
curved?
doesn't necessarily act on mass.
Yeah.
It acts on the space itself.
So like,
Yeah,
the light is going
because
to space,
maybe
like
what
normal.
gravity is
It's a
Curvature.
distortion in space. Curvature.
is
Yeah.
a change in the shape of space.
Got it.
That it isn't a force at all. That it is simply a change in the shape of the world we experience. And that light doesn't experience force. It obeys Newton's first law. It experiences no acceleration. And it travels a path that we think is curved because we're three-dimensional people and we do not perceive a fourth dimension that exists on top of us. What is the most fundamental definition of a straight line.
2 points that are connected.
Shortest distance between two
Shortest
points.
distance between any 2 points.
Oh, you're so awesome. The shortest distance between any 2 points. Now, the shortest distance between any 2 points could be a straight line to us. But if we have a fourth dimension, as your reading will show you, it could appear curved to us. Because if there is a fourth dimension, the shortest path between 2 points in 4-dimensional space-time might not appear to be straight in 3 dimensions. And that the parabolic path that you see light take is actually the 3-dimensional projection of a 4-dimensional straight line. So when you are holding an object and you drop it and it accelerates down, it experiences no force at all. It travels at constant speed through space-time along the path of shortest distance in space and time. You might have some questions at this point as to what the heck this is all about. Yeah, like this is pretty upsetting to think that gravity isn't a force at all, especially because Newton's laws are so good. I mean, think about it. What was it? When did we launch Voyager? 70s? I think so. Basically, we went like this. We got a really big gun. And we're like, all right, hold on a second. Wow! And we fired a projectile into space that we gave the exact trajectory to orbit exactly the planets we want, to turn and take pictures of those things, to know where it would be 50 years later. All with Newton's laws of physics. All with the assumption that the gravitational force from these planets and objects generates accelerations on that space probe so that it follows the path that we expect. And now we're saying that all of Newton's laws with respect to gravity are garbage. How do you think people felt about this when Einstein put it out there?
Not good.
Does anybody know when general relativity, in Einstein's life, when general relativity was accepted as seeming to be true?
In his life, wouldn't it be never?
Correct. He was dead. He was dead. He never, and you can't give Nobel Prizes posthumously, which is why there was never a Nobel Prize for relativity. They didn't believe him until he died. And he died not far from, I'm forgetting now, Einstein. What year did he die? Yeah, 1955. Quantum mechanics was fully on the scene. All of the weird stuff that you hear about with wave functions and all that stuff that we'll talk about towards the end of the year, that had already happened and was well documented. People were accepting quantum mechanics and hadn't accepted general relativity. And something truly wonderful happened shortly after his death, relating to a solar eclipse that allowed him to be vindicated. And the phone call is said to have been to the Academy of Science, gentlemen, we have a new Newton. And general relativity was finally accepted. There are still problems with it, but it is perhaps the most exciting and weird theory in physics that we have. It is well documented. It plays a huge role, Jasmine, in astronomy, as you were already hinting at. And it is essentially the theory that being in a gravitational field warps the shape of space, and that there is no such thing as gravitational force. So we will talk about that in some depth. Also, what curvature of space-time even means in some depth in the next few classes and in some videos that are upcoming. I'll ask a very dangerous question at this moment in time. Questions? Oh, Grayson. Questions? Nothing? Okay. All right. Well, I guess, is there anything else I've forgotten in here? One thing I forgot to mention a little bit earlier that is kind of useful. If when you first started physics long ago and far away, you were bothered by the fact that the acceleration due to gravity was not a function of mass, that no matter how heavy an object was, when you were very young, that no matter how heavy an object was, that the acceleration due to gravity would be the same. Almost done. Sorry. If you're upset by the fact that in so many of your physics equations in your introductory or AP physics classes were such that the mass didn't matter to the acceleration, for a ball rolling down a hill, for a projectile being launched through the air, if you kept on getting upset that the mass canceled out and didn't matter, you were keying into something very important, that it is weird that mass gets to both tell us how strong gravity is and how much inertia we have. No other physical quantity has that dual power. Charge tells you how strong the electrostatic force is, but if you had a force, an electrostatic force of QE acting on an object, mass wouldn't cancel. Charge doesn't get to tell you inertia and the strength of an electrostatic force. It just tells you the strength of the force. Color charge in nuclear physics doesn't get to tell you inertia. Why should mass get to tell you the strength of a force and how much inertia an object has? And what Einstein is saying is there is only inertia. There is no such thing as a gravitational force. It canceled because the object wasn't experiencing a force, which is kind of neat to explain why those things canceled. All right. Enjoy the reading. The Feynman stuff is really, really cool, and I will see you guys on Friday. Hopkins should be totally cleared, so I should be at school for our meeting on Friday. Okie dokie?
All right.
Mm-hmm.
Thank you.
Unless there's any questions, I'll see you guys later.
All right. Bye.
Bye.
Bye.